I think I take for granted uh, where the electricity in my house comes from. It's easy in the middle of the night when you hear a loud noise and uh, get out of bed, go to the wall switch and flick it on. The light turns on, to not give pause to where the electricity is coming from to allow the lights to glow. For a long time here in Southern California, the big portion of the electricity we got came from the San Onofre nuclear generating station, and it's that iconic two-dome structure that's right there along the ocean. And the electricity that's generated there is carried through high power lines across long distances, all through the grid. How does it work? In a nuclear reactor, there's a controlled nuclear fission reaction that creates a bunch of heat, and that heat is used to boil water. Now, this is kind of a rudimentary explanation of it, but if this represents, here, let's color this in. Here we go, we've got some flame. You get the idea. Okay, and then if we use that, we have some contained water that we can boil. Then it comes out of there as steam at high pressure. And if that steam is high enough pressure, then we can use it to turn, well, guess what? A coil of wire. Yeah, that high pressure steam is used to rotate a coil of wire that sits on an axle. And the ends of the wire contact the commutator, right, that piece of metal that has the gap in it. One brush connects here, another brush connects here. And as the axle rotates with some frequency omega, then based on Faraday's law, EMF is equal to negative N d phi dt. The faster we can get the coil of wire to rotate. Oh, and of course this coil of wire needs to sit in the presence of some external dipole magnetic field. Sure, we can generate electricity in this way. And then I guess this brush goes off to, well, one of the power lines, and this brush goes off to the other, and then we form a complete circuit. So, yeah, here, something like this. Let's let this one both go to ground and go off to one of our transmission lines. There's the poles that keep this all above ground, and then this wire goes off to the other line. Okay, there we have it. So one of the lines is connected to ground. The other one then is going to oscillate at with some EMF, and I think we derive this as negative omega n BA sine omega t. So there's a high oscillating voltage in one line. Now it doesn't go straight in, actually. We pass it through a transformer. So here, probably diagram it more like this. From the power plant, whether it burns coal or uses a wind turbine, doesn't make a difference. Both of them somehow spin a coil of wire in the presence of magnet. And then the energy is always passed through a step-up transformer. This is the beauty of AC electricity. Now you guys remember the transformer. This is a device that won't work on DC because the whole idea of Faraday's law involves the word change. There needs to be a changing flux. So if you put DC into the primary coil of a transformer, then it's only in the moment that you turn it on or turn it off that you'd get any voltage on the secondary coil. But if the input is AC, there's a continuous changing magnetic field from the primary that pushes a changing flux through the secondary coil, and you get a continuous AC output. So AC can be transformed, and the reason we want to step up the voltage goes something like this. The power that's lost as heat is found by multiplying current squared times resistance. Well, these transmission lines, they are thick metal cables. And the thicker a metal cable, the less its resistance, but you have miles upon miles of them. So even though it's really thick wire, the tremendous length of it makes for a large resistance. You guys know that resistance is resistivity times length over area. So even if it's a really big area, in order to keep the resistance low, you still have an incredible amount of length. And so the resistance in these lines is large. And power loss is given according to the formula for electrical power. It says P equals current squared times resistance. So there's no way around it. This is a large value. So the only way the power lost as heat can be a small value is if the current is really small. Well, that's what happens in a step-up transformer. It steps the voltage up, but it steps the current down. And so we transmit at very high voltages because we want to transmit at very low current. Okay, so we might step it up to hundreds of thousands of volts in these transmission lines. So by the time it gets back into the neighborhood where it's going to be consumed, it actually usually gets stepped down twice. Once at the substation, and that might step it from hundreds of thousands of volts down to either tens of thousands or maybe even just thousands of volts. And then that's carried through the city, and just outside of your home, there's another transformer on the line that steps it down from either the 10,000 or 1,000 value to a value of, well, a value of 120 RMS, or as we found recently, that's the same thing as 170 peak value. Okay. And in the end, what do we have in the home? We've got these outlets that have a neutral, a hot, and we have our own local ground wire. So the reason this one is pretty much pegged at somewhere close to 0 volts is because back at the power plant it's grounded. But it's not locally grounded, so there might be a slight difference between local ground and ground at the power station. So there's no guarantee this is exactly 0 volts. Here's a local ground, so that's for sure 0 volts. Here's the one you're interested in, the shorter prong, the one we call the hot wire. And so that one is a output that oscillates between positive 170 and negative 170 volts. Why is it oscillating? Because in the end, it's just all tied back to the way the electricity was produced in the power station, which is all tied back to the way generators work in accordance with Faraday's law. So when you have a peak-to-peak value that goes to 170, that corresponds to an RMS value of 120 volts. So now that we understand RMS value and how we send electricity and what's the sort of general design of our 120 volt household outlets, now we want to answer the question, what happens when we take the electricity from a standard household outlet and we allow it to pass through a combination of inductance, resistance, and capacitance in an electric circuit? All right, stay tuned for the next lecture.